Hi everyone. This is an example of a limiting reactant stoichiometry problem. We're going to follow our same 4 steps, paying extra attention during the second step, where we're going to be able to find moles twice and carry out this important decision, which reactant is the limiting one, which one's going to run out first, by taking our 2 mole answers and comparing them while referring to the balanced equation. Here we go. Calculate the mass of water vapor produced when 692 grams of octane reacts with 1600 grams of oxygen. We need to be on the lookout for some keywords to help us understand what the reaction is going to be. We can read the question and skip the numbers. What mass of water vapor is produced when octane reacts with oxygen? Do what we need to do to come up with a balanced chemical equation. Here, it's octane, which we can find in the data booklet if we're not quite sure what the formula is. C8H18, it's reacting with oxygen. It's a hydrocarbon combustion reaction, so we're going to produce CO2 and H2O. As we expected, water vapor was produced. We need to balance this equation. Extra care here. We have 8 carbons on either side and 18 hydrogens on either side. Let's look at what's going on with the oxygen. Here, 8 times 2, that's 16. And here, 9 times 1, 9. So we have 16 plus 9, a total of 25 oxygens on the right-hand side. So here, the coefficient for these oxygens is 12.5. 12.5 times 2 is 25. We have a balanced chemical equation. I'm going to encourage you to balance those oxygens when we're doing hydrocarbon combustion with a decimal if we have an odd number of oxygens on the right-hand side. That keeps the coefficients smaller. It saves us time instead of going through and doubling all of the coefficients to get rid of that decimal. Let's look at what we have. Calculate the mass of water vapor produced. Calculate the mass, M, of the water vapor. That's where the question mark is. That's required. We have a bunch of other information. We have 692 grams of octane. Here, the mass of octane is 692 grams. We also have the mass, 1600 grams of oxygen. We have enough information to find moles twice. As a matter of fact, we're going to do mass over molar mass twice. So first, we have the moles here of the octane. I'm keeping it right underneath this chemical. It's the mass, 692 grams over the molar mass. That's 8 carbons, 8 times 12.01 plus 18 times 1.01, which is 114.26. And we do that operation. 692 divided by 114.20. We get 6.05636, etc. moles. I'm not rounding that off, keeping it the same value. What about the oxygen? The moles is 1600 grams over the molar mass of oxygen, 32. And 1600 divided by 32 is a nice perfect 50 moles. We've balanced the equation, we've interpreted the question, we had to do a calculation, we found moles twice. Our next step is to decide which of those two reactants is the limiting reactant. I need to examine the 2 mole values, 6 and change, and 50. We need to analyze those while referring to the balanced chemical equation, which says that 1 mole of octane is going to react with 12.5 moles of oxygen. 1 reacting with 12.5. I'm going to turn that into a little bit of a statement just to organize my thoughts. The chemical equation, the balanced reaction, says we need 12.5 times as much oxygen as octane. Normally I wouldn't be writing down a little statement like that, but it helps to organize my thoughts. The equation says 1 reacts with 12.5. Well, here we have about 6. How many moles of oxygen is it going to take to react with 6 moles of octane? I can even take that unrounded answer (6.05636). If I multiply it by 12.5, we end up at more than 75. 1 reacts with 12.5, so 6 would react with about 75. But we only have 50, so we need to make a decision. Which of those 2 reactants is going to run out first? We're supposed to have 12.5 times as much oxygen as octane, but we don't. 6 times 12.5 is about 75, but we only have 50. This means that even though 50 is a way larger number than 6, when we analyze those values thinking about the equation, the oxygen is the limiting reactant. That means that it, ran out of space, is the G that we're going to use to answer this question about the water. All that work, and we're still just wrapping up step 2. After we decide on the limiting reactant, we're going to use it to do the stoichiometry. So it's a little bit repetitive because we already did this operation right here, but that was just to make our decision. I'm going to now do a regular stoichiometry using the oxygen. So that's here. It's repetitive. It's the 1600 over 32. Now it's multiplied by R over G. Here's R. We did all that work just to decide that the oxygen was going to be the G. So this is 9 over 12.5. We're trying to find the mass of the water. This represents our red N, like always. So now we're going to multiply by the molar mass of the water, 18.02 grams per mole. We can get to pushing buttons. We know that that's already 50 times 9 over 12.5 times 18.02. That equals 648.72. That's the raw answer that comes out on my calculator screen. Here, when we're thinking about the significant digits, it's slightly more involved than a different question. Even though in the question itself, there's a number with 3 significant digits and a number with 4 significant digits, our answer was based on us only using that one number, which had 4 significant digits. So I need to round my answer off to the same number, which is 648.7. And this is the mass in grams. When we have a limiting reactant stoichiometry problem, it's going to stand out. There's going to be enough information to find the moles of both of the reactants. There's lots of thinking, lots of work that goes into deciding which reactant is the limiting one. We need to look at the two mole values while referring to the balanced equation. We need to think about a statement like this. Maybe even we need to write it down. Once we make that decision, then we're going to use those values of the limiting reactant to follow through with the stoichiometry to answer a question about the product. And I hope that helps.